we need to analyze ripple tank. First of all, we need to know how this setup is going to look like, because most of you guys might not have seen these setups in your schools, right? So actually, to be honest, these setups are there in mostly almost in all the popular schools. Like popular schools means, I mean, schools with sophisticated equipments and all in laboratories, right? So in most of the schools, these things are there, right? Okay. So ripple tank is going to look like this, right? I will show you some videos also, no worries, right? So, but the diagram, I have not included the diagram in the note. So if you feel like you can draw it on your own note later. I will quickly just draw a rough sketch, right? So I'm not going to waste time on the drawings and all, right? So I'll just draw a rough sketch somewhat quickly, right? So there is this kind of a board, right? Excuse me for my drawings, right? So I'm not very good at these things. Yeah, okay. So there is a shallow cubic part, right? So a rectangular region where you can put some water. Like it's shallow, right? So not very deep. It's shallow. I'll show you, right? So this part is glass. This is glass, and this is made out of glass. All right. This transparent glass, this base. So you can fill water. You can fill water in this cubic region, right? You can fill water. So that's going to be 4 legs, right? Obviously, that should be right. It's going to have 4 legs, right? And the most important thing is exactly directly below this, there is a screen, right? Directly below this, there is a screen, a white screen. Mostly it's white screen, right? Simply directly below this, underneath the table, kind of, right? White screen. This is a white screen. So on this screen only, you can observe the demonstration of whatever the property that you're going to demonstrate in waves, right? So this white screen, on this white screen only, you're going to see the properties, right? Okay. So on the top, there is going to be so at this kind of a place, there is a bulb, right? A bulb, right? Okay. And then there is a oscillator, a vibrator. There is a vibrator. There is a vibrator and a motor connected to it, right? And a motor connected to it, a vibrator, right? This is the like, this is not the exact figure, right? So I just drew only the required parts, for you to understand, right? Okay. So the thing is, it's like this, very simple, right? You turn on the, like, you will have to fill this cubic region with some amount of water, a very small amount of water, right? A shallow. This is very shallow, not very deep, right? Very shallow. You fill that with water. All right. So from the top, a light is turned on. The light is turned on from the top, right? Next, what you need to do is you need to turn on the vibrator. You need to turn on the vibrator, right? So what will happen? It will oscillate. It will oscillate. It will oscillate. When it oscillates, what happens? You know, when there is an oscillation, a wave starts to generate. When there is an oscillation, a wave starts to generate. So what happens is a water wave starts to generate. What happens? A water wave. The water wave starts to generate. This is water waves, right? Water waves. They start to generate and they will propagate. They start to propagate. So actually, because of this light falling on this wave, on these water waves, you will be able to see some significant changes. You'll be able to see some observations. I will come to those observations, how they are going to look like, so why they look like as that, and all these things. What is the principle behind it? All these things we will analyze, but just for the time being, you will be able to observe certain observations. Right? If it is reflection that you need to observe, you can observe the reflection from the white screen. If you need to observe the refraction of wave from the white screen, you can observe the refraction. If you need to observe the diffraction, you can observe that. If you need to observe the interference, you can observe. So all these properties of waves, which we are going to talk, right, can be observed through this ripple time. Very, very important, right? So this is it. Okay, so how these things form. Now I guess you are pretty. It's understood, right? How the setup is going to look like, right? So yeah. So what happens is, now I'm going to show you how this demonstration takes place. There were some bright regions, there were some dark regions. Bright regions, dark regions. Let's see how that kind of a observation falls on this white screen. Right? Okay. So when we consider, back to physics, right? When we consider a wave, a water wave, when we consider a water wave, it's going to look like this. It's going to look like this. The surface. This is the surface. Surface of the water wave. So it moves now. So these are called what? Crests. These are called troughs. Crests, troughs, crests, troughs. We have discussed about this in the previous session, right? So yeah, previous session. So guys, the bulb is directly above. So it's directly above, right? It's directly above. So light rays falls directly onto this waves, water waves. It falls directly onto these water waves. Let's consider two waves which falls onto a crest. Let's consider two light rays which falls onto a crest. What will happen? What will happen? A crest can act in this. So this is all levels, right? So not optics. What I'm going to talk now is not from optics. It's basically from O levels. If a light ray falls on a bulged out surface, if a light ray falls on a bulged out surface, it will converge. It will converge. this will act as a convex lens. It will this crest will act as a convex lens, which means the light rays are going to converge. If the light ray converges to this point, that denotes that there is a bright region. Due to this light ray being converged onto certain lines, certain points, only you observe the bright lights. So how do you explain the dark regions? When a light ray falls onto a trough, when a light ray falls onto a trough, what happens? What happens? This trough acts very similar to that of a concave lens. Concave lens, right? So bulged in. That is the case. The light ray, what happens? The light ray will diverge. The light ray will diverge. So is the light going to fall onto this point? No. This point is dark region. This is a bright region. Dark region, bright region. But yeah, okay, that's fine. Okay, wow. Now we know the concept behind dark and bright. So, but we observe as lines, right? So lines of dark, not points, lines. So what might be the reason for that lines? This is it. The light ray that falls onto these troughs directly below a dark region, sorry, bright region. The light ray which falls onto this wave, once again, bright region. The light ray which falls onto this wave, the crest of this wave, light region, bright region. Sorry. So guys, when like there's not only this like it's not a finite number, it's just plenty of waves. It's uncountable number of waves are going, right? So those lines form a bright region. Those lines form a bright region. Bright region. So the lines that falls onto this kind of point, the lines that falls onto troughs, lights that falls onto troughs, once again they will form a dark region, because light will not penetrate, I mean it's not going to come down, it's going to diverge out, which means there's no light in this region. There is no light to be observed in this region, directly below the troughs. Directly below the troughs, no light. But at a crest, light. Trough, no light. Crest, light. Trough, no light. So this is why you observe side by side dark region, bright region, dark region, bright region. This is the reason. So, I don't know whether we could explain that simpler than this, right? We know these things and all. Okay. This bulb. We call it as like for this bulb. When it comes to a ripple tank, right? When it comes to a ripple tank, as the bulb, we are not going to use a normal bulb, right? We'd be using some kind of a sophisticated bulb that is, we call this as stroboscopic bulb. We call this as stroboscopic bulb or stroboscopic lamp. Why do we call that as a stroboscopic lamp or stroboscopic bulb? It has the ability to blink. It has the ability, this light, the lamp or the bulb that we use in a ripple tank has the ability to blink to any frequency that we set. We can set the frequency of this manually. Frequency means how often should the bulb light per second, how many times should it blink, frequency. For 1 second, how many times should it blink, frequency. We can manually set that. Okay? We can manually set that. So these are the things what they ask in experiments. Like once they ask a certain question, so they might ask, they do test whether you guys have done these practicals, right? So they assume, they expect you guys to know these factors, right? As the lamp, we use a stroboscopic bulb, which has the ability to blink according to a certain frequency. So that's it. Why do we need a bulb like that? It's the problem. So if there's no purpose, so useless, right? So why do we have to use this kind? We can straight away use a normal bulb, right? So, but why do we use this kind of a bulb, right? So now I'll ask you a question. So keep this question in your mind, right? So keep this question. Why do we use this bulb? You will come up with an answer when I explain further, right? You need to remember this question then. Why do we have to use a stroboscopic bulb in ripple tank experiments? Okay. So guys, now we can observe this kind of wavefront. Okay, this kind of waves, this kind of observation on the screen. Light region, bright region, dark region, bright region, dark region, right? So it's going to be like this. Bright, once again bright, once again bright, once again bright, likewise, right? So I'll just draw this in this way, right, for you to further understand. Bright region, dark region, bright region, dark, bright, dark, bright, dark. So now, if I ask you a question, now I need to find the wavelength of this water wave by using this. First of all, before we come to that, you need to know that there's plenty of bright lights, which means when all these bright points, which converges from a large number of waves, when all these light, when all these points are connected, the line that we obtain is called as a wave front. This kind of a line is called as a wave front. So guys, is this a wave? It's not a wave. It's a wave front. This is formed due to a lot of crests, lot of light rays that falls on lot of waves. There's not only one wave involved in forming this kind of a line. There's plenty of waves involving in forming this kind of a line. So that line is called as a wave front. Wave front. Wave front. Wave front. Right. So the line that passes perpendicular to this is called as the ray. The line that passes perpendicular to the wave front is called as the what? Ray. Ray. So these are wave fronts. Rays. Rays. Right? So one thing that you need to understand is this wave front is formed due to what? Think about this. So all these have the same gap, right? So although I have drawn it in different gaps, all these wave fronts are going to be in the same gap. There's a lot of waves involved. If I ask you a very simple question, I need to find the wavelength of these water waves. I need to find the wavelengths of these water waves by physically by means of a ruler. By using a ruler, I need to measure the wavelength. Can I do that? By using a ruler, I need to measure the wavelength. Can I do that? So if you take the ruler and then go and measure this, it's not going to be still, right? It's going to move. And then also it's something impossible for you to do, like to measure the wavelength of a water wave by placing the ruler in a ripple tank on this water surface. It's not going to be possible. But there is an option that you have. That is, by using these wave fronts, you'd be able to find the wavelength. By using these wave fronts, there is a method for you to find the wavelength of the waves. What is that? So we know what is the definition of a wavelength? A wavelength lambda means distance between 2 points which are in same phase. Same phase. The minimum distance between two adjacent points. Okay, sorry. Two adjacent points. Two adjacent points which are in the same phase. So this is the water wave. This is one point. This is another point. These 2 points are in the same phase, right? Isn't it? Both are definitely in the same phase. It is in the same phase, right? So how do I demonstrate that? Okay, when you get this, right? So this is 0 phase, 90, 180, 270, 0, 360, once again 90, once again 180, likewise it repeats. We have discussed about this. Those 2 points are in the same phase. So the distance between two adjacent crests means one wavelength. The distance between two adjacent crests means one wavelength. So this is one wavelength. One wavelength, lambda, right? One lambda. So what does that confirms you? The distance between two wave fronts is one wavelength. The distance between two wave fronts is one wavelength. Distance between two wave fronts is one wavelength. All right, very important. Right. Okay. So now what you could do is, now you can take your ruler, go to the screen, place the ruler on the screen, and measure the distance between two bright regions or two dark regions. It doesn't matter. Measure the distance between two bright regions or two dark regions. Oh. So you can find lambda. Can you? These are progressive waves. Progressive waves means they are propagating waves. So what happens is, when this continuously happens, when this vibration continuously happens, the wave continuously propagates forward. When the wave continuously propagates forward, this wave fronts also along with that propagates forward. If the crests are moving forward, this bright region should also move forward. It's moving forward with a larger speed, higher speed. So you can't go and keep this and then measure. It's not going to be still. This waveform, this pattern, it's not going to be still. It's not going to be still on the screen. It's going to propagate forward. In that case, once again, a difficulty. We need to find some mechanism. Somehow, if we can make this waveform, still, if we can make them look like still, actually we can't make them still. That's pretty obvious, right? So because when you vibrate, they are going to propagate forward. You can't actually make them still. What you can do is, you can make them to look like it's still. You can make these wave fronts to look like it's still. How do you do that? Now it's the question. So we are going to capture the points using the blinking bulb, since they blink with equal time intervals. So we're going to capture the points using the blinking bulb, since they blink with equal, kind of. You have came very closer to the answer. If you think more in detail, you can figure that out. Like you can't use cameras and then take a photo, and then it's not going to be in scale, and then those things. That is not how experiments are done, right? Matching the light frequency with the wave frequency will make them functional mix. Exactly. That's the answer. Right? That's the answer. What you need to do is to make them look like it's still. What you could do is, now it's like this, right? When this light, okay, so this denotes that the light is turned on. Okay? So when the light is turned on continuously, you'd be able to see the wavefronts. It's moving forward. What you can do is you can adjust the frequency of the bulb, the stroboscopic bulb. You can adjust the frequency of the stroboscopic bulb such that the frequency of the stroboscopic bulb is equal to the frequency of the vibrator. Is equal to the frequency of the vibrator. So it's like this. If the vibrator has 2 Hertz frequency, if it has 2 Hertz frequency, that means what? 2 waves propagate per second. 2 waves propagate, 2 waves are propagated per second. Now, you make the frequency of this also 2 Hertz. This will be turned on. This will be turned on twice within 1 second. This generates, for example, right, 2 Hertz. 2 Hertz means this generates two waves per second. This blinks twice per second, twice. So it's like this. When the first wave comes, it lights. Then when the next wave comes, once again it lights. So it's like, try to think in detail, right? Imagine these things, right? So because it's very hard to explain without demonstrating these things. First wave comes, like bulb turns on. When that wave goes, shuts. When the next wave comes, turns on. So it shows the waves to be still. First, it showed the first wave front. Then it stopped. Next, when the next wave came, like it doesn't show the moving of the second wave, first wave. After the first wave reaches, only once again it starts. The bulb starts. Then it looks like it's still. If you did not understand the concept, just remember what you're doing is, by your stroboscopic bulb, you are making the frequency of the stroboscopic bulb equal to the frequency of the vibrator. So in that case, you can make this look like it's still, but actually, all right. So this is understood. Now, guys, now we know how to measure the wavelength. How to measure the wavelength? Simply, the stroboscopic bulb's frequency should be equal to the frequency of the vibrator. In that case, the image will stop. It will look like it's stopped, right? So in that case, quickly we can measure the length between two bright regions or 2 dark regions, and then it's going to be equal to the wave length. And so it's right. What happens? What happens if I erase this? Right? What happens if you use a pointer to vibrate like this? For example, now in the, like, as the vibrator in the first case, what you used was a plain rod. But if you use a pointer, it's kind of a pointer, right, on the repel tank, right? What happens is, right? What happens is on the screen, right? You will be able to see. So the wave fronts will move how? This is one wave. This is another wave. This is another wave. This is another wave. This is another wave. This is, so likewise, all these crests, joints, these troughs, joints, these crests. So you will be able to see. Circular wavefront. You will be able to see circular. You simply circular wavefronts, right? So if this moves up and right, this moves up and down, you'll be able to see circular wavefronts below the repel tank, right? I guess you can figure it out, right? So the water falls on this point, the bright region, likewise. It's in and out, circular wavefronts, right? These are circular wave fronts. So how about the waves? The waves will move perpendicular to the circular wave fronts. Right? Always it should be perpendicular. Okay. Ray. This is what we call as incident ray and all, like refract. We come to that. Right. Ray. Ray is going to look like this, perpendicular to the wave front. Right? Perpendicular to the wave front. All right. Now, let us come. This is what happens. This is the basic story of a repel tank. This is the basic story of a repel tank.